Picture a blazing hot day. A kid crushes an ice cream cone to cool down, but by that evening, they're running a fever. Our brains are hardwired for patterns, so we immediately link the two events. The ice cream obviously caused the fever. It feels perfectly logical. But in the realm of scientific research, that instinctual guess means absolutely nothing. To strip away personal bias and find what is actually true, researchers have to transform that random guess into a formal, testable architecture. They have to build a hypothesis. The core problem researchers face is that reality is remarkably messy. Millions of intersecting events happen every second, generating endless coincidences. Looking at this node diagram, we see how science establishes a baseline against that chaos. This is the null hypothesis, the default assumption of zero connection between eating ice cream and spiking a fever. To push back, researchers formulate an alternative hypothesis, claiming a provable relationship actually does exist. A researcher's entire methodology, from gathering data to running equations, serves a single focused purpose: structuring enough undeniable evidence to defeat the null hypothesis. But how do you actually build that evidence? You have to start by stripping the scenario down to its core elements, known as variables. This diagram shows the simple hypothesis. It begins by isolating exactly one cause, like eating the ice cream. We call this the independent variable. You then measure that isolated cause against exactly one effect, the fever. That is your dependent variable. This rigid one-to-one mapping gives researchers a highly controlled environment. It allows them to track a direct line from action to reaction without any outside noise. The catch is that the real world rarely operates in a clean vacuum. Environments shift, and new factors constantly bleed into the equation. To mirror reality, researchers upgrade to a complex hypothesis. We introduce a second independent variable alongside the ice cream, like freezing weather. Because causes scaled, outcomes scale too. Dependent variables expand from running a fever to measuring school absenteeism. The math is no longer a straight line. Researchers now have to calculate how these overlapping, compounding factors interact with each other in real time. Defeating the null hypothesis becomes significantly harder when you juggle multiple variables. Yet this complexity is exactly what allows scientists to draft an accurate blueprint of how life actually works. Once that blueprint is drafted and the variables are locked in, researchers have to evaluate the results. They do this through two distinct lenses. First is the statistical hypothesis. This is the mathematical burden of proof required to verify that the connection between the ice cream and the fever is a reliable pattern, rather than blind luck. But equations only solve for the numbers. We also need the practical hypothesis. This lens evaluates the physical toll of those variables, like a sick child missing from their desk on a Tuesday morning. Statistics prove the connection is real. Practicality proves the connection actually matters. By carefully stacking these variables and passing the mathematical tests, a researcher achieves their ultimate goal. The null hypothesis is defeated. The relationship is proven. If the data shows that the ice cream caused a fever for just one specific kid, we have what is known as an existential hypothesis. The claim is true, but it is deeply localized to that single instance. Science rarely stops at a single instance. The ambition of research is to test those localized results across wider populations and totally different environments. Looking at this matrix, we see how the evidence scales until it reaches the universal hypothesis. This is a structural rule that applies to all variables, everywhere, at all times. We live in a world overflowing with noise and coincidence. Hypotheses give us the strict architecture required to cut through that chaos. They are how we stop guessing at reality and start proving its undeniable laws.